Hey guys, in today's video I'm going to be covering breadth first search and the queue data structure. Before I talk about breadth first search, I'm going to talk about the queue data structure because it is imperative to how breadth first search works. So the queue data structure is pretty intuitive. It follows a FIFO principle, or first in, first out, and you can think of it as a line or a waiting queue. Some of the operations that you do to a queue are you enqueue, where you add an element to the end of a queue, or you dequeue, where you pop the element from the front of the queue. You can think of a queue as a restaurant line, where the first one there is the first one that leaves. So now I'll talk about breadth first search. Breadth first search is a fundamental sorting algorithm, and breadth first search differs from depth first search because depth first search searches in a vertical manner, and breadth first search searches in a horizontal manner. That will become more evident as I show how breadth first search searches every vertice on this graph. Breadth first search is great for finding the shortest path between two elements on a graph, because the shortest path is discovered immediately as soon as the node or vertice has been visited. So I'll start off searching the graph at 1. I will mark the vertice gray when it is added to the queue, and then I will mark it as green when it has been visited. So I'll start off by marking 1 as visited, and when 1 gets visited, we add all of its neighbors to the queue. So I'll add 2 to the queue. And then we visit 2, mark it as green, and then add 3 and 11 to the queue. From here we will then visit 3, marking the unvisited neighbors to the queue, add 4 to the queue, and add 10 to the queue. And then we go to the next vertice that we added to the queue. Because of the FIFO principle, first in, first out, 11 was added to the queue before 4 or 10, so we visit 11 next, and then add its unvisited neighbor nodes to the queue. Then we move to the next node in the queue, 4, mark it as visited, add its unvisited neighbors to the queue. Then we move down the queue and we visit 10, then 9, then we visit 12, and then we visit 5, then 6, adding its unvisited neighbors to the queue, and then we visit those neighbors. And that's how breadth first search would explore all of the different vertices on this graph. And hopefully from that, you're able to see how it explores the graph in a horizontal manner. Instead of digging down one particular path, it explores all of the depths of the paths in a breadthward or horizontal manner. And where it has an advantage over depth first search, like I mentioned above, is it always finds the shortest path to the node as soon as the node is visited. So whereas with depth first search, depending on how you enter the parameters, it could find node 5 by going 1, 2, 11, 9, 10, 3, 4, 5. But with breadth first search, it will always find the shortest path to 5 as soon as the node is visited. So now I will explore the graph again while showing the queue and how the solution evolves as we explore the graph. I'll start at element 4 and I'll add the smallest element to the queue first. There are many valid solutions for BFS. You could add the largest element to the queue first, the rightmost element, the leftmost element. All are valid solutions to BFS. So I'll start at 4 by visiting it and adding it to the solution. Then I'll add its neighbors to the queue. In this example, the top of the queue is the head of the queue. This is where I will dequeue from, and the bottom of the queue is the tail of the queue. This is where I will enqueue from. So now let's explore 3 because it is at the top of the queue, and we will dequeue that and visit it, and then add its neighbors to the queue. Then we will move on to the next node in our queue, which is 5, and we will visit it, and we don't have to add anything to the queue because it has no unvisited neighbors. Now we move to 6, visit it and add its neighbors. Then we move to 2, we visit it and add its neighbors as well. Next vertice is 10. Then 7, then 8. We'll mark 1 as visited, dequeue it and add it to the solution. And then we'll visit 11 and add its neighbor to the queue. Next is 9. And finally 12. And we'll remove it from the queue and add it to the solution. You know that BFS is done running when the queue is empty, so when implemented in code, you would run a while loop and say while queue not empty, run BFS. And if you ran that operation on vertice 4, adding the smallest vertice to the queue next, this would be your BFS solution for this graph. So that's an overview of BFS and queues. I hope you enjoyed watching and have a good day.